Great. Good to see you all again. Thank you for coming back. Welcome to the second lecture in the series on dependently typed functional programming in Idris. So I've given you the introduction yesterday. I've given you a sort of quick run-through of all many of the features of Idris. Today I'm going to talk about, today and tomorrow I'm going to talk about things you can actually do if you have a dependently typed programming language. In particular today, I'm going to talk about one of the things that interests me most, which is implementing embedded domain-specific languages. So it might seem strange, I suppose, to implement a programming language just to have another language to implement other languages in. But hopefully by the end of this lecture, you'll see why that is a valuable thing to do. So I'm going to start with just a little bit of history of programming languages and abstraction. And then we'll go on to one of the kind of the hello world examples of dependently typed programming is the well-typed interpreter. So this is an interpreter for a simply typed lambda calculus where programs just by their existence are proof that they are type correct. So I'll show you an example of that. Then we'll go on a bit further and I'll show how to make it more easy to program in these kinds of embedded languages. And one thing towards the end of how we can use embedded domain-specific languages to do resource correctness proofs. So when I talk about resources, I'm talking about things like file handles, memory usage, locks in concurrent programming, the kind of things where if you mismanage them for whatever reason, so if you mismanage locks in concurrent programming, say you might end up taking too many locks, you end up with deadlock. So I'm going to show some possible approach to managing that kind of situation. So just to start, let's talk a little bit about what we mean by languages and abstraction. So in computer science, we're always talking about abstraction. So as far as normal people are concerned, English speakers, abstraction is this is the definition I got from the dictionary. Is the process of considering something independently of its associations or attributes. So as far as computer science is concerned, that's just this is a definition I got from Ron Morrison's PhD thesis. So Ron Morrison was the former head of department at St Andrews University, so still around, an emeritus professor, retired now, but our old head of school. This is the best definition I found, best computer science definition I found was from his thesis. It says, a process of extracting the general structure to allow the inessential details to be ignored. So it kind of reminds me of when I was learning about computing back in the 1980s. There was a series of very nice books on how computers worked for children, the kind of things you don't really seem to get anymore. They're published by Osborne, and you might be able to find these on eBay somewhere, I suppose. And one of the things I remember about them is that they illustrated computers by having little robots running around rooms, putting ones and zeros into pigeonholes. And in my head, that's still how computers work. Does anyone else remember these books, or is it just me? One person remembers these books. Okay. Good. I'm glad I didn't just make them up. I'm glad it's not a figment of my imagination. As far as I'm concerned, when I press the button on this slide show, the little robot in here is making a telephone call to the little robot in my computer. That's abstraction. It's about having, little robots running around the computer. Okay. A computer system really is just a series of layers of abstraction, starting right down at the sort of microcode level and then moving up to the way we communicate with it. This is a computer. This is a very early computer. Anyone recognize this one? Yes. Guess who's been on Wikipedia getting the public domain pictures? That's ENIAC, yes. So ENIAC was, according to Wikipedia, so it must be true, was the first general-purpose electronic computer. And Turing complete, which means that you could use it to solve any computable problem, but it didn't have any abstraction. So if you wanted to if you wanted to actually solve any problems on it, you had to move wires around and flick switches, and hopefully you'd get it to do the thing that you wanted it to do. So as far as computing power is concerned, this Mac here and that ENIAC we saw before can solve exactly the same problems. It's just that we probably need an ENIAC the size of the planet to implement Idris, but in theory it's still the same computing power. So later on we get stored programs, so we get EDSAC, programs stored in memory as binary data. Obviously that gets tedious after a while. Sticking the ones and zeros in pigeonholes like our robots in our little children's books. So along comes assembly language. This isn't EDSAC assembly language. This is, I think it's PDP-11 assembly language, which I've picked just because it's a very easy one to read. So you've got mnemonics for machine instructions, and you've got human-readable notation. So we've already gone 2 levels of abstraction up from our moving wires and flicking switches around. Okay, quiz time. You must all recognise this. This woman, yes. This is Grace Hopper. In our story, she's very important because, well, she was very one of the designers of COBOL, if I remember rightly. We forgive her for that because she did many.
Mama COBOL.
Sorry, was that?
Her nickname was Mama COBOL.
Mama COBOL. Right. Okay. She also came up with A0, the first compiler. Not really a compiler. It was more a sort of linker loader. So that converts the specification into machine code. And she did this, apparently, she said, because she was lazy, and she hoped that the programmer might return to being a mathematician. So basically, it's all about laziness. Everything we do is about laziness. Making new abstractions is about laziness. It's so that we can write down exactly what we mean, so we don't have to do the work of telling the computer all the details of what we mean. We just want to tell it exactly what we want to do. Just as an aside, supposedly, again, this is according to Wikipedia, so must be true. She popularized the term debugging. So this thing here is a moth that was found in a machine, and the comment there says first actual case of bug being found, and apparently extracting this from the machine led to the phrase debugging. This is probably not true, but why let the facts get in the way of a good story? So moving higher level still, we get to Fortran. We've got familiar mathematical notation, so we're getting closer to programming languages we know and love. Invented by a team led by John Backus, who later won the Turing Award and gave a very nice lecture about can programming be liberated from the von Neumann style, where he waxed lyrical about the promise of functional programming. So obviously we forgive him Fortran for that. He also said, it's the L word again. Much of my work has come from being lazy. I didn't like writing programs, and so I started working on a programming system to make it easier to write programs. That's really what we're doing all the time here. That's everything that we're aiming towards with higher level languages and domain-specific languages, is making it easier to write programs for your actual domain. I mean, we love, because we're computer scientists, we love writing programs for their own sake. But outside of our ivory tower, people actually like to get things done, apparently. This is why we like to make it possible to run programs, of course. The active programmers in the corner are looking astonished again. So yes, after Fortran, we get more and more high-level languages, and I've picked a selection here for various reasons, providing new abstractions. So C being an abstraction over the operating system, I suppose. Go I've picked for no reason other than I like playing the board game Go. And when it was announced, I saw something on Reddit that said, Go programming language. And I thought, brilliant, someone has finally made a domain-specific language, and it's possible to express strategies for Go. This will be fascinating. And then I was very disappointed. But still, it's an interesting new language that, if you haven't looked at, is worth a look. So there's a lot of programming languages around. And yeah, I'm sort of going to give the rest of this lecture about how to make even more of them. But this is an interesting observation made by Peter Landin way back in 1966. Has anyone read this paper, The Next 700 Programming Languages? A few people. If you haven't read it, I would suggest you go and read it. It is a great piece of programming language research history. There's quite a lot of papers begin with the words "the next 700" now as well, if you're talking about sort of generic ways of doing things. One thing he said in that is, it's very early on in the paper, so it might even be the opening sentence of the paper, is that most programming languages are partly a way of expressing things in terms of other things, and partly a basic set of given things. So if we can come up with some generic way of describing things in terms of other things, and then give a specific set of given things, that specific set of things is basically our domain knowledge. That's how we write domain-specific languages. So, higher level still. This is where we're getting into more modern times. A domain-specific language is just a language that allows you to express things in a particular problem domain. Typically, they work at a very high level of abstraction. So, as far as possible, you just want to write, what you need to know to get the job done. So typically declarative. You just say what you want. You don't say anything about how to do it. And they're quite often not Turing complete. And if a domain-specific language is Turing complete, it might even be, by accident. Actually, it's quite surprising how many things are Turing complete. Send mail configurations, they're Turing complete.
The Intel MM-Boot
What was that?
The Intel MM-Boot Handler.
I didn't know that. Wow.
HTML5 and
Okay.
ES3 are
Right, so it's actually harder to think of things that aren't Turing complete, I suppose. Coq is not Turing complete. Well, even that's not strictly true. Anyway, let's not go into that now. So a few examples. So you've all programmed in DSL, of course. Database applications, HTML, R, Mathematica, so if you're doing scientific programming. Unreal script, so quite a while ago now. So a domain-specific language for a particular computer game. Also, I reckon this is a kind of domain-specific language. So if you use email filters in your email client, this little dialog box that you describe email filtering in, is certainly a domain-specific language. It's certainly a language because you have a set of rules that you describe. It's just that it doesn't have textual syntax. You don't have to have textual syntax to be a language. Or a music playlist. So any kind of configuration for software is also a kind of domain-specific language. So we see these things all the time, high-level expressing kinds of domain knowledge. So, one thing I'm aiming to do in Idris is to support the implementation of domain-specific languages that you can verify, that you can say strong properties about. And I'm going to start with something that's, a lot simpler than any of these highly specialized languages. I'm just going to do an implementation of the simply typed lambda calculus. So, is this a language or formalism that we're all familiar with? Is anyone not familiar with this? Don't be shy. Okay, so everyone's happy with that. So I'm going to show you just how to describe the syntax in Idris and describe an interpreter for that syntax in Idris. And then I'm going to show a little bit about how to make use of the Idris type checker to get the typing rules automatically for your DSL. So I'm going to start with something a lot simpler. It's the simplest possible language I could think of to illustrate how to write an interpreter. And this is something you could do in Haskell as well, or any kind of functional language. So our expression language here is we have values, which are integers, and we have a way of adding two sub-expressions. So to write an interpreter for that expression language is pretty simple. We just say, okay, we'll write an interpreter that takes an expression and returns an integer. If we have a value that's x, we just return it. And if we want to add one expression to another, we'll interpret the left-hand side of that, and we'll interpret the right-hand side, and then we'll add the results, and then we're done. Brilliant. So it's quite hard to write. The type system for this language is very simple. Everything is an integer, and so if every sub-expression is an integer, then there's no problem with adding two integers together. So everything here is going to be well typed and well scoped. There's no variables. So let's make it a bit more exciting. Let's add variables. So I've just got strings for variables. And so if we're going to interpret expressions in this language, it might go wrong because the variables that we use might not exist. So to interpret programs in this language, we're going to have a context mapping variable names to integers. So we've got here a list of pairs of strings and integers and an expression, and that returns maybe an integer, because if something goes wrong, if we look up a variable and it's not there, then we'll have to have some kind of error. So again, just as before, if we got a value, we just return it and we ignore the environment. And adding things up, we interpret the left one under the environment, we interpret the right one under the environment, add them up. And if we have a variable, that's where something more interesting happens. We have to look up the variable name in the environment. If it's not there, well, we've lost. If it is there, then this is a type error actually. This is what happens if you every case doesn't return maybe. Yes, thank you. This is what happens if you type things into a slide without running them through your type checker first. So if we want to write if we want to write an evaluator for this language, it might return an error, and in this case, it'll return an error before we even run it. So, to write something, what we want to do is write an interpreter that only allows us to write well-typed expressions, well-scoped expressions, where all the variables we have we know are in scope, where every expression we have we know is well-typed. And we want to add more than just integers and more than just addition. We want to have functions, we want to have abstraction, we maybe want to have let binding. And in order to do that, we have to think about what types our language is going to support. So I didn't go any further with this, partly because I already made a type error, and partly because I started thinking about how to do application of sub-expressions to each other, and really it gets quite boring because you have to do a lot of dynamic checking that the thing you have is in the right form. You have to check that, for values, you can have values being integers or booleans or functions, so you have to start thinking about what the structure of values is as well as the structure of expressions. And I thought, well, forget that. Let's just move on to the dependently typed language where we can express the types in some generic way. We can compute the result type of the evaluator, and we can do things rather more precisely. Okay, so now starting to work on the full simply typed lambda calculus. So the types we have available, I'm going to allow two kinds of primitive types. I'm going to allow integers and I'm going to allow booleans. And I'm going to allow function types. So this is, you can read this as a function arrow. So it's a function from this type to this type. So remember I mentioned yesterday that in a dependently typed language, types are first-class citizens, which means you can calculate types just like you can calculate any other value, any other kind of function. So what we're doing here is we're translating object language types. So I'll refer to, it gets a bit awkward when you're implementing languages. You have to start disambiguating the language you're implementing and the language you're implementing it in. So when I'm talking about the language being implemented, I'll refer to that as the object language. And when I'm referring to the language we're implementing it in, typically refer to that as the meta language. So in this case, Idris is the meta language, and this language we're talking about, this is the object language. So what we've done here, we've defined the object language types, and interp_ty is a function that translates object language types into meta language types. So we're going to write this interpreter basically by translating object language programs into meta language programs. So interp_ty translates object language types into meta language types. For tyint, that just returns an integer, just returns int. Tybool just returns bool, and tyfun st returns the function type from whatever s was to whatever t was. So this is obviously never going to get run, this program, not at runtime anyway. This is going to get used by the compiler because we're calculating types. Types get erased at runtime. So it's going to get used at compile time to calculate the type of the rest of the program, basically. Everyone happy with that? I see some nodding. Good? Yes? I see a little bit of confusion. Mostly nodding. Don't be shy about asking questions if there's anything a bit strange going on here. So a few more preliminaries we need before we get to the actual implementation of the language. So there's a bit of an aside. This data type, fin, is the type representing finite sets. So finite sets are just sets that contain a finite number of elements. So fin of 0, that's the finite set containing 0 elements, which is obviously the empty type. Fin of 1, finite set containing 1 element, and so on. So I can represent this by saying, well, f0, that is the first element of a finite set of k plus 1 things. So I can always have the 0 thing as long as I have k plus 1 things available. And if I have an element of a set of k things, then its successor is going to be an element of the set of k plus 1 things. So actually, although I've called this the finite set, I could just as easily have called this bounded numbers, and it would have kind of meant the same thing. So this is a good way of representing numbers with an upper bound, which is quite convenient if you happen to have a vector of a certain length. So we have here an element of a finite set bounded by n, and we have an element of a vector that has n things in it. So the bounds of these things are the same, which means that we know from the type of this index lookup function, there is no way that this number can ever be out of bounds, because its bounds are the same as the bounds of the vector. So the 0 thing, looking at the 0 thing and a vector of containing x cons x's, that gives us x. Looking up the successor of kth thing, well, we get the kth thing from the tail, and that's going to be fine. Now you'll notice that we haven't dealt with the empty vector here. So why do we not need to deal with the empty vector here?
Impossible.
It's impossible. Why is it impossible? I've put an n there, so that n could be 0 upwards.
N gets instantiated to successor of something.
Yeah, so n is going to get instantiated to successor of something, because there's no way, in fin n, there's no way that n can be 0, because neither of these constructors allows it to be 0. So because neither of these can have the index 0, there's no point in checking for the empty vector, because well, we've already ruled that out. Do you have a question?
So if you swap the fin and the vec
Right.
in the argument, will it still totality check?
Yeah, it'll be fine, because the way the coverage checker works is basically generating all the other possibilities from the cases that you've given, and checking them all. And if any of them type check, it says, hang on, you've missed one out here. And so basically all of the other ones have to fail. So in this case, it will be checking F0 empty list, FS empty list, and it'll see that neither of them unify, because one has to have a successor index, one has to have a 0 index. Right, so this means we can do bound safe lookup. We can know at compile time that a lookup isn't going to fail, so we know we don't have to do any of the checking that we did incorrectly on our simply typed version before. Now, why did I show you that? Well, it's about the way we represent variables. So earlier we represented variables as strings, just because that's the quickest way to represent variables in a quick hack of an interpreter. But actually, in practice, it's better to refer. I find it's better to refer to variables by how you're going to look them up in a context. So you have a context of types and values, and we represent variables just by their position in that context. So this is it's called a de Bruijn index. If there are any Dutch people in the room, because whenever I say de Bruijn index, Dutch people find that hilarious, because I can't do it. And I've been told that I shouldn't even try. But,
De Bruijn himself told me to call him De Bruijn.
Right.
Since it is the German word, the German name Braun.
Right. Well, British people normally just say brown in a similar kind of way. Anyway, so there's a Bruijn index. It doesn't have a name. It's just a number that counts how many binders, how many bindings ago it was defined. So you got this expression lambda xy dot x plus y. Well, this x was defined 0, 1 binders ago. This y was defined 0 binders ago. So you just say lambda xy dot first thing plus 0th thing. So this takes a little bit of getting used to. But it's a very easy way to implement the interpreter. So you'll have a first step that translates your name into an index, and then your next step will just work with the index. So if you have n variables, then fin n is going to represent a bounded de Bruijn index. So if you have 0 variables, then clearly there's nothing in that vector, fin 0. There's nothing there. So if you have a context G that is your vector of length n, and you have an index I, which is your element of the finite set with the same bounds, then this is a bound-safe lookup. Index IG is a bound-safe lookup of that variable in the context. Right. So this is the first step towards implementing representation of a language where we can't possibly have variable lookups that fail. Right, so let's get on to a little bit of code. Now, remember this using notation from yesterday, by the way. This just means that every time we see this G in this block of code, it's going to mean that G is a vector of types. So this vector of types represents the types of all of our local variables that we have available in our expression language. So, if we have a vector of types, then we're also going to need a list of values that correspond to those types. So when we're interpreting our programs, we're going to need to actually have access to those values. So this environment is indexed over a corresponding list of types. So it's a heterogeneous list, basically. It's a list where every element in the list has a possibly different type, which is determined by the types in another list. So if you have an empty context, so nil here, then you must also have an empty environment. If you have no local variables available in your type, then there's no point. You clearly can't have any variables. If you have a context with a cons g, the context of a cons g, so something of type A and then the rest of the context, then you must also have an environment for the rest of that context, and the value you have must be whatever type this A says it is. So we have an actual value here that is given by the type of A. Yeah? Is that people happy with that? Now, this has type predicate is kind of what we were doing with lookup on the or index on the slide before. It's just that instead of representing it as a function, I've written it down as a predicate. I've written it down as a predicate because I just find it easier to work with. It's kind of let me see when we get to the implementation why I think it's easier to work with. But this is just similar to the list membership predicate we had yesterday. It's just slightly lifted up. It's a context membership predicate rather than a list membership predicate. So given some index I and some list of things, so a fin n and a vector of n things, the zeroth thing in the context t cons g has type t, so this is just a statement. It's a sort of, like before, prologue style statement that the zeroth thing in this context is t. And then if we know that the kth thing in context g has type t, then we also know the successor of kth thing in a context extended by u must also have type t. So this is kind of a weakening rule that if you add things to a context, then what you have is you still have the same type. So I've called these constructors stop and pop, which means that you can read again. You can read these just like natural numbers. So pop of stop is 3, the third thing. Just like there of here was 3. S of 0 is 3. We have a lot of different ways of writing down numbers, don't we? Pleasingly, it's possible to translate them all to machine integers if you think carefully when you implement your compiler. So you don't actually have to worry about the internal representation of these things. They are just numbers. But they're very informative numbers. They're numbers that don't not only tell you what the number is, they tell you why they're that number. And if you want to prove things about your programs, which is, after all, why we're all here working with dependent types, is if we want to show that our programs actually work, you do have to do a little bit of additional work to explain why your number is a number. It's the number it is, but the machine will at least translate it to something a bit more sane. Right, so that's context. So just to illustrate this, hammer that home a bit more, this is what an example might look like. So we've got a vector of two things here, an integer and a boolean. The corresponding environment is going to have an integer and a boolean in it. So the environment that corresponds to this context, 42 true, so we've got an integer and a boolean. And then a context membership proof, so proof that the second thing in that context is a boolean would look a bit like this. So the successor of zero thing in context is type bool. Well, the proof just looks like pop stop. So we're representing variables by counting by the Brown index that counts basically by saying the number of pops that we're going to do to get that variable. Right. So let's have a look at the actual interpreter. Let's see it running. I know this one type checks because I've done it. Right, I'm in the right directory. Yes, good. So as before, you have all of this code available. So this is in the course code.pgz if you want to play with it later. Right. So go back to the top. We've got our interpty that we just looked at. We've got our definition of environment. So we've got a lookup function that, given some index and given some environment, returns the right type. This lookup looks remarkably like the index function we had before. So it's just the ordinary list lookup. And right, now we have, having gone through all that, we have our description of what an interpreter might look like, or a language might look like. So a variable, so before we had a variable being just represented by a string, here we have a variable represented by a context membership proof. So if we know that the ith thing in the context G has type T, then we have an expression that has type T. So you can kind of read these as typing rules almost. If you look at it in a sort of sideways way, you can see that this is, gamma proves expression has type T. So value, I've just got integer values. That's an expression of type integer. Now lambda, so we're working in a nameless representation. We're working with the Brown indices. So for a lambda, what we do is, for the scope of that lambda, we extend the context G with something of type A. So we have an additional variable available in the body of that lambda, and that gives us a function type, function from A to T. So corresponding to that, if we have a function type from A to T, and we have an expression of type A, then applying that gives us the expression of type T. Here I've got arbitrary operators, so you can just embed any operator that from the Idris language that works with expressions of the appropriate type. So I could do maybe addition or less than, all of the things we might expect, provided that we can work out what A, B, and C are in the object language. And then finally, just to make it possible to write slightly more interesting programs, I've got a conditional, so if expressions. Right. I haven't, however, written the interpreter for this. Now, the way we write the interpreter is, the reason we've gone through all of this effort to write down the types of the language and work out how to translate object language types into meta-language types is so that we can write an interpreter that simply translates to host language, meta-language programs directly. So given an expression of type T, what the interpreter is going to return is an Idris expression that has the representation of that type T. So if I look at, for example, the type of var case, that's not very helpful. Well, actually, it is very helpful because it tells us that it's going to be whatever the type of this the variable sub-expression is. So how's this going to work? Well, it's the type is going to be, we're going to have to look up the ith thing in the environment we have available. So the only thing we can reasonably do is look up the ith thing in the environment. And yes, that type checks. That's good. So let's look at the type of val case. What does that give us? Well, we've got, you'll see that if I duck. So we've got an integer. We need to return something of type interpsi of integer. So that suggests that all we have to do is return this x. Yeah, happy with that. Lambda is a bit more complicated. We have an expression in scope here that has some there's going to be some function. Well, we're going to have to build some function type, and this scope is going to have to do something with the variable that we introduce into the environment. So I'll just do this one quickly. So we're going to have to make a function. The only way we can make a function is with a lambda. So let's make a function with a lambda. And given that introduces a new variable that we can pass to the interpretation of the scope. So let's interpret the scope with this x stuck onto the front of the environment and interpret the scope. Yeah? Let's see if the machine agrees. Good, that's reassuring. Application, well, what are we going to do? Anyone want to shout this out? How do we interpret an application? We've got two sub-expressions to interpret, which suggests we're at least going to have to interpret f and interpret s. So you're suggesting interpret f and apply that to the result of interpreting s. Yeah? Great. We haven't done any error checking yet. Isn't that wonderful? For an operator, well, we're going to have to interpret x and we're going to have to interpret y, and given that our operator just applies the result of that, it should simply be that. Yes, good. Thank goodness for that. And if then else, well, same. All we're doing is directly translating to the host language equivalent expression. Then I didn't actually need the brackets there, did I? Put that on a new line. I'm really having to resist laying that out more neatly for the sake of getting through this. So that's all. Happily, that's all works. So, well, we should probably test this, shouldn't we? Would that be? Yeah, I know. I've got a few test programs here now. As you can see, these are perfectly reasonable programs that are perfectly sane to write. You just have to be able to write in the underlying syntax. Now, if you're a Lisp programmer, you probably don't mind doing that. Well, I think you probably don't like using the Brown indices for your variables, but apart from that, you just have to write in the underlying syntax. And the biggest one I have here is this factorial program. So I've got a laziness annotation here because otherwise it would interpret the function forever. So I have to interpret the function lazily just to make sure that the factorial function doesn't run forever. And it's quite a neat way of doing unit testing in a dependently typed language. So this type so, let's write down the definition. Oops, oh, so true. So it looks a bit like this. The only way of constructing something of type so, you can only construct something of type so true. It's impossible to construct something of type so false. So this means that the only way this program is going to type check is if the factorial of 4 through our interpreter really is 24. So let's find out. It did type check. I realise I've not shown you anything that doesn't type check today. So as far as you're concerned, I might have fiddled this so that it always works. So, well, that's reassuring. It can't unify so true with so la. Specifically, can't unify true with false. Well, that's a relief. We're glad it can't unify true with false. So yeah, if you're one of these people who likes unit testing as well as types, and you probably should be one of these people who likes unit testing as well as types, because although you can know that your program is going to work, sometimes it's a good idea, as I say, to test that it really does work. Then we do have this rather extreme way of doing unit testing. Let's comment that out. Oh, I suppose we could compile and run it, and it'll print 24. So yay! Now, problem here is that I can't really reasonably claim that this is a usable embedded domain-specific language, because you're not going to come along and start, well, you're not going to program in this language because it's just a simply typed lambda calculus. But let's assume that we take it a bit further and we make it a more, a more useful language, which we will do in a little bit from now. To assume we've done that, you really want to have, well, this is neither readable nor writable, I suppose. That's the problem. Remember I said yesterday, programs are for humans to read, only incidentally for machines to execute. This is a program that's for a machine to execute, and it's not really for any other purpose. So, fortunately, there's a lot of fairly obvious structure here. So lambdas introduce variables, and we got variables all over the place. Stop here, pop stop here, and we have in our host language we have lambdas. We have binding forms. So it would be nice if we could somehow exploit what we have in the host language to make the object language more readable. So, what do we do? So here is the same interpreter. So same language, same implementation, but after defining expressions, we explain what it means to be a program in that language, what it means to sort of write down a program. So this DSL construct says, right, okay, we're going to have a new language called Expra. And in that new language, lambdas are going to be represented by lam, variables by var, and then index first and index next tell the system how to construct the Brown index from a specific variable. Which means we can now say, under an Expra, we can now use the Idris construct to build programs in this language. I've added a few more things. So this is this dollar. If you're familiar with applicatives in Haskell, this just gives you this is how we construct functions under idiom brackets. So this under idiom brackets, you automatically get this dollar form. We can also add new syntax rules. So this syntax construct says if the parser sees something in this form, then translate it to something of this form on the right-hand side. So in square brackets, that indicates non-terminals, and anything that looks like an identifier is considered a terminal symbol. So this just adds a new production to the grammar, basically. Now, obviously, this is clearly possible to abuse. Please don't do that. I think it could be argued that I'm abusing it here, by the way. So I've added a couple of top-level definitions. So I've overloaded the equals and less than operators, and it's perfectly reasonable, I think, to make our expression language parameterized by integers. So integer expressions in our object language, I think it's perfectly valid to make that an instance of the numeric type class, because, well, they are numbers. We just have a different way of writing them down. So I've got, so plus is just the operator plus, minus the operator minus, and so on. So that's our interpreter again, so just like we had before. And now our programs look a little bit more like actual programs. So these are exactly the same programs as before, just with the mechanical translation from this form to the original form. And so this lambda turns into a lamb in our object language. This x turns into the appropriate variable. We've got an x and y here, so this turns into stop, pop of stop. This turns into just stop. This y turns into stop. And I have the same unit test to make sure that it actually really still is the program. So I've used idiom brackets in the implementation of factorial. So under this else, we're using the application. All the idiom brackets mean here is that use the application from the object language rather than using the application from the host language. So now we have an object language program that actually, I mean, you still probably don't want to write in this language, largely because it's just a simply typed lambda calculus. But at the very least, you can look at this and believe that it is the program that you say it is. So that DSL notation is just a way of making more readable programs and slightly more writable programs. Yes, question?
So I noticed that you didn't define the applicative operators as an instance of the applicative type class.
No, it might actually have been possible here.
So idiom brackets get translated directly to the name of the operators without putting any type constraint.
Yeah. Cool. And I've done that entirely because it makes it easier to do this sort of hack. I wouldn't necessarily encourage doing it without thinking carefully about whether it's the right idea, but it's something that's available. It means also with do notation, you don't need to have a monad to use do notation. And if you're doing something that's quite a complex DSL, you probably don't want to make all of your languages an instance of monad just to be able to use do notation. So I think it's a shame actually in Haskell that do notation and monads are so firmly, so strongly related. But there you go. That's just my opinion. Right. So that's a pretty simple DSL. It's not a particularly useful DSL. The domain is simply programs that are harder to write than programs we can already write. So we should probably think about how we might want to use this kind of method. So before I do that, just I'll briefly go through what all the syntax overloadings were. So DSL notation is you can also have let in here. So let allows you to overload let binding. Otherwise, you have variables, and you have basically how to construct variables and how to redefine binders. So I think it's quite a lightweight notation and quite powerful, although also something that if you're not very careful could go wrong. So do take some care with it. We're also allowed to introduce new syntax rules. So this is how if then else in Idris is built, by the way. And it's also how the range syntax that we used yesterday. It's also how the range syntax is built. So a lot of syntactic sugar is something that you can construct using syntax rules rather than having them baked into the parser. So this is a bit of a contrived example for loops. But as well as having non-terminals here, you can also mark binders. So the fact that this X is in braces here means that X has to be in a binding position on the right-hand side. So we can make a for loop in the Python-style syntax by saying, okay, we've got for X is a binder in some list, and then a colon, and then the body, and that just translates to an application of this for loop function, where this X on the left has become a binder on the right. So there might be some situations in particular DSLs where that's a useful thing to do. There's one in the exercises, in fact. And one more thing, this one definitely should be used with care, is implicit conversions from one type to another. But so Scala people love this sort of thing, having implicit conversions for implementing domain-specific languages. You often find that you have a constructor just because you need a particular sub-expression form, and it's quite obvious which constructor you mean when you write the program. So what I've got here is a language that has a val constructor. This is just some arbitrary language. I don't know what else this language does. And an implicit function underneath that says, okay, if you've got something of type insert IA and it didn't type check, well, try just inserting this implicit coercion and see what happens. So they're very restricted, these implicit coercions, because they're obviously potentially quite error prone. So you can only ever have one at a time. The system will not chain implicit coercions. It'll just try applying one. And if there's any situation where there's multiple possible implicit coercions available, it will use none of them. So you have to decide carefully which ones you really want, and ideally set it up so that only one will ever be available at any given time. We're going to see a case in Thursday's lecture where this is absolutely vital to making things usable. But in general, I'm mostly showing you this because it exists. So I would not encourage using it unless you really have a good reason. Before I show you the resource thing, I want to do a little bit of an interlude, because this is the only time I can think of where it really fits into the course, of how to call foreign functions. Because I've said that Idris is a systems programming language before, and what I mean by that is that you can do operating systems interaction without too much difficulty. The way to do that is by obviously being able to call C functions or foreign functions from Idris programs. It's quite neat, I think, that we didn't actually have to change the parser or add any high-level language features in order to do this. We just had to add a little bit of a tweak to the compiler. What we can do is describe foreign functions in Idris syntax just as it is, and we can describe foreign function types because, of course, we can compute types from descriptions. You just saw that with interpty for our expression language. So we describe foreign types just as basically a universe of types. We have foreign integers, foreign floats, foreign characters, and so on. This fne is I wouldn't worry too much about that at the moment. This fne basically is translate it directly into the Idris runtime system representation. So if you want to do some particular kind of low-level hackery. fptr, that's a void pointer. So if you have something like, I don't know, a file handle or any kind of C data structure that you don't want to manipulate in Idris, but you do want to be able to pass around, that's what fptr is all about. And funit is typically used for void functions, C functions that don't return anything. So obviously, like before, we can translate these foreign types into Idris. So the obvious translation, fint becomes an int, float becomes a float. Obviously, the runtime system has to know how to do the marshalling, but that's where the magic comes in. This is not something we have to add to Idris itself. Essentially, what we're doing here in Idris is modeling foreign functions, and it's the compiler's job to work out how to run the things. But it means we can write down C function types, and we can translate them into an equivalent Idris function type. Yes.
FPTR, we take to PTR?
FPTR becomes PTR. PTR is just it's a primitive type that you can't make in Idris. There are no constructors for PTR. The only way you can ever get one is from a C program. So to build a foreign function call, we have this function foreign type, takes a list of input types and an output type, and returns an Idris type. So I didn't give the definition of this on the slide, but you can probably imagine that all this does is it constructs a function from all of these things to one of these things. That's all. Then a foreign function call is a string, that's the function name. It's a list of the input types, an output type, and that gives you a foreign function of some type. And then finally, this make foreign, this is not defined. This is in the library, the type is in the library, This is the only magic. It's quite a lot of magic, but it's the only magic. It's the only magic function. This is compiled specially. So any compiler backend will need to be able to implement make foreign for this to work. By the way, as of last night, there is a Java backend for Idris. It's in the GitHub version. I haven't actually tested it because for some reason Mac and Java don't mix very well. I don't know if there's anything going on there, but anyway, I'm told it works. Any backend that you implement, so the JavaScript backend, does your JavaScript backend do something special with this?
The JavaScript backend works with the foreign function stuff, yeah.
Yeah, so you have to do something special for make foreign, I guess.
Yeah.
Yeah. Okay. So as far as you're concerned as a programmer, writing foreign functions, you just do things in this sort of form. To make a function from string to IO something, just use make foreign. Put through, this is defined in the runtime system. Takes a string and returns a unit. You do have to fully apply them, unfortunately, just because of the way make foreign is compiled. So I can't drop X out here, which is slightly annoying. But and then getting a character, well, that just doesn't take an argument and returns a character. So a more complicated one is if we're dealing with files. So a file is just some file handle and then a pointer. This is a pointer that we get from C. So to open a file, we have this raw function that just returns the pointer. So it calls file open with a string and another string for the mode in which we're going to open the file and returns some pointer. And then we have this little wrapper open file that mode is a higher level description of the file access mode, which could be read, write, or read, write. By the way, something I forgot to mention yesterday is that unlike Haskell, you have to write top-level type declarations for Idris functions because type inference and dependent types don't mix in general. However, in this case, it's completely obvious what the type of mode string is going to be from its first use here. Obviously this position here has to be a string, and the mode we already know. It's a file mode, so we don't need to write a type declaration for mode string. So otherwise, in general, you do need to write type declarations. But for simple things, there is a clear definition of what I mean by simple things. I'm not going to say what it is here because it's a bit long. Typically, you'll need a type declaration, but here you didn't. Right, now, final thing for today, I'm going to talk about a more practical use of this DSL approach. And it arises from this is a quote from Joe Armstrong, who designed Erlang, and this was said by Joe to my colleague Kevin Hammond in a pub in Tallinn. So if there's anything that is more true than what you hear or what you read on Wikipedia, it's what you heard from a man in a pub. So this is clearly true. Nobody in industry cares whether a program does what it's supposed to do. They just care with how it behaves when it's run. So, if your program gives the wrong answer, you just sort of, fiddle and try again. If it crashes, well, that's kind of annoying because you've got to reboot. You've got to restart your software. You've got to download the new version. This is something that particularly they care about in the Erlang community because they're very interested in keeping things running. So this is extra functional correctness rather than functional correctness. So the distinction we make between functional correctness and extra functional correctness is functional correctness is about does the program do what it's supposed to do? So, does your sort function return an ordered permutation of its input? Does x plus y always equal y plus x? That kind of thing. Is your list lookup always bound safe? Extra functional correctness is more about does the program run within the required resource constraints? Does it manage resources correctly? Does it run within a megabyte of RAM? Well, the answer is, I believe, always no these days. I had a student, by the way, who we were doing. This was just the other day. This is completely off topic. I'm going to tell you anyway. They're learning C, and I told them not to use getS for reading strings because of the possibility of buffer overflows. And this student said, I use getS, and it's okay because I initialized the string array with maxint characters, so I knew it wouldn't be possible to overflow. And I said, great, you don't have a buffer overflow. The only problem is I want to run another program while you're reading your text. So It was a novel approach to the problem, though, and I'm glad I'm glad they're thinking about it. Anyway, so this is a kind of extra function. So functionally, it was clearly correct. This extra functional question of is it going to run within a reasonable amount of memory? Well, maybe not. So I'm going to go through the simplest possible resource example that I could think of, basically because it's very easy to understand files. And it's actually very easy to get them wrong if you're not very careful. So any program which manages files has to use files in a way that conforms to a simple resource usage protocol. So informally, before you read or write a file, that file has to be opened, and that open has to have succeeded. So if you open a file and it didn't work, well, actually you typically just plow on and assume it did work, and then things will go wrong. But you have to make sure it's worked, and you can't do any, it doesn't make sense to work with the file before it's been opened. If you have opened a file for reading, then there's no point in trying to write to it, vice versa. And when you finish processing, you should be closing the file, because if you keep files open the whole time and your program is running all day, then you're going to run out of file handles. So what we're going to see now is a domain-specific language extending this idea of the simply typed lambda calculus interpreter, but which encodes, in general, a resource usage protocol. So we're going to be separating, just like Peter Landin said, we're going to be separating the basic set of given things from the way of way of expressing things in terms of other things. So this is going to be the program that we end up writing. This is a resource-safe file management program. It looks a little bit like monadic I/O. Looks a little bit like monadic I/O. There's a couple of differences. So this isn't I/O here. So if you're a Haskell programmer, you'd expect to see I/O at the top of an I/O program. This is res. This means it's res resource safe. And we've got a little res here that suggests something funny is going on. Now, if you've been paying attention, you'll probably realize that this res is defined using DSL notation, and something funny is going on underneath. The fact that this program type checks, it does type check, by the way. This one I have tested. This one does type check. The fact that it type checks means that it is a valid implementation of the resource protocol that we were talking about. So if I forget to close the file, for example, it isn't going to type check. Or if I try to open it twice, it's not going to type check. Or if I don't have this thing that checks whether it opens successfully, it's not going to type check. But you can't see any dependent types in here. What we're really aiming at here with implementing domain-specific languages is using dependent types to make sure that everything works, everything is managed correctly, and there are no possible runtime errors behind the scenes, but having a language in which someone who just wants to write programs can get things done. So a programmer using one of these DSLs really shouldn't have to understand what a dependent type is in order to be able to do something useful. Right. So last thing for this lecture, I'm going to show you fairly briefly how this works, because it is quite an involved example, and if you really want to get the details of what's going on underneath, you'll probably have to stare at it for a little bit longer than we have available. Right. So it's in your course code directory again, and it's the file res program, and it makes use of the resimp module. So there we are, type checked, and there is the program, just to prove that it's this program that type checked. So what happens up the top? I'll work backwards again. I'll start at the program and I'll work backwards towards the DSL. So we're going to define why we're opening files. So we're opening them either for reading or writing. Just for the sake of simplicity, I've left read write out here. And instead of files just being a file handle that could be in any state, well, file handles are file handles that are open for some purpose. File handles exist for a reason. They exist to be either read or written, and if the file is closed, then the file handle doesn't exist. That's basically what we're saying here. So opening a file, well, there's this mysterious creator ID here. This basically means this is an I/O function which makes something new, and it makes either something broken, it makes either an empty tuple, or it successfully makes the file handle. So we've got a bit of checking here. We open the file. This is just the underlying raw file open thing. If it's a valid file, so this basically means if it was successful, then return the file handle. Otherwise, return just the empty tuple. So we also have updaters. So close updates the status of something. So given a file on the way in, it gives something empty on the way out. So that just closes the file. And then we have readers, and these are things which neither create nor update. They just keep something in the same state. So end of file is also a reader. A little bit of sneaky syntax overloading here. So we're working in a DSL that allows you to apply creators, updaters, and readers. So closing a file is an updater, reading a file is the user, end of file test is just a user using a resource. And then, possibly not surprising to notice that if opened is also a bit of syntax overloading. It's kind of cheating there. But check is basically the if then else of our resource language that will take something of type either, and it will pick the branch according to what was in the either, but it will carry through the evidence that it's in the right branch. So when you go into this branch, we'll have the evidence that the file exists, and when we go into this branch, we'll have the evidence that the file doesn't exist. And then we have the program. So what does the language itself look like? Well, this is the language itself. I've been good to you here. I've even written comments. So like before, we're parameterized over an environment, or context of the types we have. The difference is we're consuming things. So we're working with resources, so things are in a different state as we go through the program. So we have types on the way in and types on the way out. So this is where the resource magic really happens. So let binding takes something that creates a new resource. So it's got to be a creator function, so like open. So when you open something, you're just passing into a let binding. So you'll have noticed that we had a let binding here. So this open has to be a creator. And then it creates a new, the scope of this is a new resource program where on the way in, we have something of type A, and on the way out, we have something that's been eaten, basically. So this type here of the scope of this let binding says you can do whatever you like with that, with the rest of the context, as long as by the time we get out, you finish with the thing you just created. So you always have to clean up after yourself in this language. What updaters do is, given some proof that we have something of the right type in the context, update it to the new type. So we've got something that goes from A to an updater of B, just update the value of type A to a value of type B. And users, well, they just don't do anything to the context. So GAM on the way in, GAM on the way out. That's all the resource magic here. The rest of it is just control structures to write programs more easily. So we can list arbitrary I/O actions. We can do dynamic checking. We've got while loops, and then we've got return and bind because that just gives us do notation for free. So the rest of this is just it's the expected thing. It's the interpreter is exactly as before, exactly the same style as before. That we just translate the program that we've got into the host language, the object language program into the host language program. I've done a little bit of trickery to do continuation passing style because it's just a neater way of passing through, returning two results at once, I suppose. And then eventually, the final bit of magic is DSL notation. So we just said, well, okay, whenever you've got a variable, well, actually, I've represented variables. I don't have a specific constructor for variables here, but I do have specific constructors for building context membership proofs. Whenever you see a let, instead of using the Idris let, use the object language let. And whenever you've got to see this res, well, just turn it into a resource program that has the same set of resources on the way out as on the way in. Question? Yes.
Is there any checking of the DSL thing?
Well,
it replaces start and part without, and then checking.
Yeah, so this happens before type checking. So, if you do something here that doesn't make sense, you're going to get a type error. It might be a slightly mysterious type error. By the way, actually, I would love to be able to describe this DSL notation in terms of type classes, and I haven't quite figured out how to do it. So if anyone can work out how to do it, that would be rather fun.
This would give types to this for.
Yeah, so basically, like you can have, do notation that you can describe as a monad type class, although I'm not sure that's the way I would like to do it. But it would be nice if you could have some kind of DSL type class where you could explain all of these things. I'm not sure it's really necessary, but it would be nice. It would be just, this is somewhat ad hoc, and it would be nice if you could explain it in a more principled way. I don't know if it's possible, but it would be nice if someone worked out that it was. Okay, so that's all I have for today. The exercises you have for today are all about implementing new constructs for DSLs. They're implementing an imperative DSL. It's rather simpler than this resource language, but slightly more complex than the evaluator language. I would also say, though, if you didn't get through all of yesterday's exercises and you'd like to carry on with them, then that's perfectly fine too. Please, don't rush ahead if you haven't quite got earlier things yet. One more thing, just one final thing. Normally by now, if someone says, "What happens if you don't close the file?" You were about to ask that, yeah, okay. Well, this is what happens. You get an error message. So the way error messages are presented, you might have noticed this, is they tend to be presented in two forms. So you get a full one that says the whole thing that went wrong during type checking, and then you get a cut down one that says the specific thing that went wrong during type checking. Now, it's not always clear which one of those is going to be more useful. In this case, well, you see this first one, and I can tell you how to read that. You read that as saying, "It went wrong." This second one is a little bit more helpful, because it says, well, you were supposed to have a unit thing, but you had a file that was open for reading. So we've got to the end of the block, and we don't have the file. So that's what happens. Right, okay, I'll stop there, and let's have a tea break, and get back to the hacking. Okay, thank you.